Albert Einstein, one of the most influential physicists of the 20th century, was born in Ulm, Germany, in 1879. While not considered a prodigy in his early years, a spark of curiosity ignited within him at the age of 5. A pocket compass piqued his fascination with invisible forces, a wonder that would fuel his lifelong pursuit of understanding the universe. Despite an aptitude for mathematics, the rigid discipline of the German education system clashed with his independent spirit. This conflict with authority figures would become a recurring theme throughout his life. In 1880, the Einsteins moved to Munich, where Albert continued his education. He devoured popular science books and independently explored advanced mathematical concepts. Despite his intellectual curiosity, he chafed at the rigid structure of formal education. This period also saw him encounter influential scientific and philosophical movements of the late 19th century. Isaac Newton's laws of motion and universal gravitation, and James Clerk Maxwell's unification of electricity and magnetism, laid the groundwork for Einstein's groundbreaking work. Additionally, philosophical movements like positivism, emphasizing verifiable observation and reason, resonated with his scientific approach. However, the prevailing scientific paradigm remained rooted in a fixed and deterministic universe governed by Newtonian mechanics. Einstein, with his inquisitive mind, would soon begin to question these established notions. In 1895, Einstein failed the entrance exam for the prestigious Swiss Federal Institute of Technology in Zurich, ETH Zurich. He enrolled at the Swiss Federal Polytechnic School in Zurich, now ETH Zurich, the following year, focusing on mathematics and physics. While excelling in these subjects, he continued to chafe at the rigid structure. He found intellectual stimulation in discussions with fellow students like Marcel Grossmann, who shared his passion for theoretical physics. In 1900, Einstein graduated with a teaching diploma in mathematics and physics. However, securing a teaching position proved difficult due to his unconventional views and lack of formal recommendations. While working as a clerk at the Swiss Patent Office in Bern, seemingly mundane surroundings ironically provided the perfect space for Albert Einstein's intellectual fermentation. The year 1905, often referred to as his Annus Mirabilis, remarkable year, saw the culmination of years of study and independent research. During this time, Einstein published 4 groundbreaking papers that revolutionized physics, each deserving a closer look. 1. The photoelectric effect, March 1905. This paper challenged the prevailing wave theory of light. Through his analysis of the photoelectric effect, Einstein proposed that light does not behave solely as a wave but also exhibits particle-like properties. He introduced the concept of light quanta, later named photons, which possess both wave and particle characteristics. This challenged the long-held notion of light as purely a wave phenomenon and laid the foundation for the development of quantum mechanics. Understanding the photoelectric effect. To comprehend the significance of this discovery, it's crucial to understand the photoelectric effect itself. When light strikes certain materials, such as metal plates, it can eject electrons from their atoms. However, the classical wave theory of light struggled to explain several key observations. Threshold frequency. Only light exceeding a specific frequency, known as the threshold frequency, could eject electrons. Lower frequencies, even with high intensity, produced no emission. Kinetic energy of ejected electrons. The kinetic energy of the ejected electrons depended solely on the light's frequency, not its intensity, as predicted by the wave theory. Einstein's explanation. Einstein proposed that light consisted of discrete packets of energy called photons. Each photon carries a specific amount of energy determined by its frequency. When a photon strikes an electron, it transfers its entire energy to the electron, ejecting it from the atom. The higher the frequency of the light, shorter wavelength, the more energy a photon carries, resulting in ejected electrons with higher kinetic energy. This explanation elegantly explained the observed behavior of the photoelectric effect, reconciling the wave and particle nature of light. 2. Brownian motion, May 1905. This research provided crucial experimental evidence for the existence of atoms, a concept then still debated in the scientific community. Einstein analyzed the random, erratic motion of microscopic particles suspended in a liquid, known as Brownian motion. He demonstrated that this movement could be attributed to the constant bombardment of these particles by invisible molecules of the surrounding liquid. Investigating Brownian motion. Brownian motion had been observed for over a century, but its explanation remained elusive. Robert Brown, in 1827, first documented this phenomenon while observing pollen grains suspended in water. These particles exhibited a seemingly chaotic, zigzag movement even in still water. Einstein's explanation. Einstein applied the principles of statistical mechanics to explain Brownian motion. He proposed that the observed haphazard movement resulted from the constant collisions of the microscopic particles with the much smaller and more numerous molecules of the surrounding liquid. These collisions, while individually undetectable, collectively produced the observed random motion. By analyzing the relationship between the observed movement and the properties of the liquid and particles, Einstein was able to calculate the size and number of atoms present, providing strong evidence for their existence. 3. Special theory of relativity, June 1905. This groundbreaking theory revolutionized our understanding of space, time, and motion. It challenged the long-held Newtonian concepts of absolute space and time and introduced the revolutionary concepts of time dilation and length contraction. Redefining space and time. According to Newtonian mechanics, space and time were considered absolute and independent entities. Time flowed at a constant rate, and space was a fixed, unchanging backdrop for all events. However, Einstein proposed that space and time were not absolute but were woven together into a single entity called spacetime. The speed of light, then considered a constant, became a fundamental limit in this new framework. Time dilation and length contraction. Einstein's theory proposed that the perception of time and space is relative to the observer's frame of reference. Objects moving close to the speed of light experience time dilation, meaning their clocks appear to run slower compared to stationary observers. Additionally, length contraction occurs, meaning objects moving close to the speed of light appear shorter in the direction of their motion compared to their stationary length. Experimental confirmation. Initially, the theory of relativity seemed counterintuitive, yet subsequent experiments have confirmed its predictions with remarkable accuracy. For example, high-precision clocks aboard airplanes flying at high speeds have been observed to run slightly slower compared to identical clocks on the ground, confirming the phenomenon of time dilation. 4. Mass-energy equivalence, September 1905. This famous equation, E equals mc squared, emerged from the special theory of relativity and demonstrated the equivalence of mass and energy. It states that mass, m, and energy, E, are different forms of the same entity, and they can be converted into each other according to a specific exchange rate represented by the speed of light squared, see superscript 2. Understanding the equation. The equation implies that a small amount of mass can be converted into an enormous amount of energy, and vice versa. The speed of light, c, is a very large constant, approximately 3x10 meters per second. Squaring this value results in an even larger number, highlighting the immense amount of energy contained within a small amount of mass. Impact of the equation. E equals mc squared had profound implications for various fields. It provided the theoretical foundation for understanding nuclear reactions, where tiny amounts of mass are converted into tremendous amounts of energy, as seen in nuclear power plants and atomic bombs. The equation also holds significance in astrophysics, explaining the energy output of stars and the formation of black holes. The significance of the Annus Mirabilis. The 4 groundbreaking papers published in 1905 established Einstein as a rising star in the world of physics. These revolutionary ideas challenged established paradigms and opened up new avenues for scientific exploration. Despite working in a seemingly mundane job at the patent office, Einstein's intellectual curiosity and dedication to research led to groundbreaking discoveries that continue to shape our understanding of the universe. Beyond the papers. It's important to understand that these 4 papers were not isolated achievements. They stem from a deeper foundation of theoretical work and intellectual struggle. Einstein's earlier studies in thermodynamics, statistical mechanics, and electromagnetism provided the groundwork for his groundbreaking contributions. Additionally, his keen interest in the philosophical implications of scientific theories and his ability to think creatively and challenge established notions were crucial factors in his success. The Byrne years and beyond. The intellectual ferment of the Byrne years laid the foundation for Einstein's continued scientific journey. He continued to refine and develop his theories, delving deeper into the complexities of gravity and the quest for a unified field theory. While his later years presented personal and political challenges, his dedication to scientific inquiry and his unwavering pursuit of knowledge remain a lasting legacy. Conclusion. The Annus Mirabilis of 1905 stands as a testament to the power of human ingenuity and the pursuit of knowledge. It serves as a reminder that even within seemingly ordinary surroundings, extraordinary discoveries can be made when fueled by curiosity, critical thinking, and a relentless passion for understanding the universe. The remarkable contributions of Albert Einstein continue to inspire generations of scientists and thinkers, reminding us of the power of questioning the established and venturing beyond the known to explore the unknown. Einstein's later years were marked by both personal and professional challenges. As a Jew living in Germany, he faced increasing anti-Semitism during the rise of the Nazi regime. In 1933, he made the difficult decision to leave Germany and eventually settled in the United States, where he continued his scientific work at the Institute for Advanced Study in Princeton, New Jersey. Despite personal struggles, Einstein never lost his passion for scientific inquiry. He continued to explore diverse areas of physics, engaging in debates on quantum mechanics and advocating for a unified field theory. He also actively participated in public discourse, urging for peace and international cooperation in the face of the looming threat of nuclear weapons. As the atomic bomb demonstrated the destructive potential of his mass-energy equivalence equation, Einstein expressed deep regret for its use. He became a vocal advocate for nuclear disarmament and world peace, using his remaining years to speak out against the dangers of nuclear weapons and the arms race. Albert Einstein passed away in 1955, leaving behind a legacy that transcends the scientific realm. His groundbreaking theories revolutionized our understanding of the universe, and his pursuit of knowledge and dedication to peace continue to inspire generations. Although his quest for a unified field theory remained unfulfilled, his contributions laid the foundation for further advancements in physics and cosmology. Conclusion. Albert Einstein's life and work offer a captivating exploration of scientific genius, unwavering curiosity, and the pursuit of a deeper understanding of the universe. He challenged established paradigms, sparked scientific revolutions, and left an indelible mark on the history of science and humanity. His commitment to truth, intellectual freedom, and peace serves as a lasting inspiration for generations to come.